The problem I decided to do was heating up a bottle of milk for my daughter. I chose this because I've always been amused by how when you have a water bottle in your car and it's warm around on a hot day and you take a drink out of it, how some of it will be warm and some of it will be cold. I thought about doing that, but I felt there were too many uncontrolled variables, and as I looked at it, we heat up bottles every 3 to 4 hours for our daughter, and so I could look at that and see how long it takes to heat it up to the right temperature. To heat up a bottle of milk, you take the bottle with milk in it and you put it inside the measuring cup. The milk starts at about 10 degrees Celsius, and the water in the measuring cup, for the purposes of our experiment, was 80 degrees Celsius. And in theory, your water will cool down and your milk will heat up. And I predict the graph will look something like that. And one reason we put the milk into a measuring cup of water to heat it up is so you don't get hot spots and ruin the nutrients inside of the bottle for the baby. We also know in theory that it's going to heat up the outside edge. That milk's going to rise up, and then colder milk's going to filter in, and it's going to heat the milk up through the convection inside. I thought this would be a fairly simple problem, lump capacitance, quick and easy calculations, but after talking to Brother Danes, I found that it was going to be multiple lumped capacitance because the water was not just losing its heat through the plastic bottle into the milk, but it's also losing the water through the glass into the air. And so we had to set up two equations, one for the heat transfer to the milk and one for the heat transfer from the water to the air and to the milk. To conduct the experiment, I was struggling to get all the data points. So I took a phone and I started the timer when the water hit 80 degrees, and I dropped the milk in and it started at 10, and then by videoing it, I was able to pause my video every 15 seconds to get a good timestamp to create a nice graph. Right here, we have our timestamp. Then we have that the experiment milk started at 10 degrees Celsius. The water started at 80. Then we said the calculated milk temp was 10, and the calculated water temp was 8. And we started and we ran them through our equations. We did the experiment by pausing the video. I did the calculated by running it through an Euler's method. And we can see that the actual experiment resulted in milk at 37 degrees, which is body temperature, and the water ended up being 64.5. Then in our model, it predicted that the milk would be 36.2 degrees and the water would be 63. The model wasn't that far off. Here we have a graphical representation of what's happening, and we can see that the experimented water and the calculated water are very close to each other on the chart, and towards the end they started to get off a little bit, and then we can see that the milk had a little bit of variation from our calculated, but in the end they met back up and they were close to each other. For fun, I took the calculated model and I just ran it all the way out until they hit equilibrium at close to the same temperature as each other. I did not do this with the milk because it would have been a waste of milk for my daughter to eat, and so our model predicts that it would be 450 seconds to get to that point. Some of the challenges I faced were when I first plugged in the equation, I put a plus sign in where a multiplication sign would be, and I saw that we were just getting straight lines, and that was not an accurate representation. Once I found that plus sign, and I changed it, I found that the milk followed the curve that we would expect, but the water did not. And upon further investigation and thinking about this, I realized that the thermal conductivity of the water, or the K, would be changing every time the temperature changed. So in my Excel sheet, I created a function that was able to interpolate based on what temperature the water was and create the graph to become more accurate. And thus we get this curve, and we see that we predicted the water temperature would be going down at a rate, the milk would be going up at a rate, and they would eventually meet. And we can see from our experimental data that the milk went up and the water went down. And I predict that this curve right here is because of the heat going in faster when the milk was cooler and had a different K value, and the water was more accurate on because I was also able to use the K values I found for the milk were in a journal that I used, and I was able to use water values out of the book. But overall, our model was a good representation of the heat transfer into the bottle.